Hi, this is Mr. Mitchell. We have a slideshow video on earthquakes. First, let's talk about a fault. One of your terms is going to be fault. A fault is a break in the lithosphere. Now, you may remember that the lithosphere is the crust and the upper part of the mantle. This is the hard stuff, the rock. And you can see here an example of a fault. You have a crack just going right down through here. And you can see even that it has moved. You see how this little area right here probably was connected with this little area at some point. And this is a good example of a fault. Another term we have is stress. Stress is the force exerted at the fault. And you probably saw stress back here. You saw that there was a force exerted at this fault right here. But a sudden increase in stress is what causes an earthquake. Now these plates are moving constantly, but whenever you have stress upon them, when you have that force exerted, that's when you have that earthquake. And most earthquakes happen along tectonic plate boundaries. And you know there are tectonic plate boundaries off our United States west coast, which happens to be where 80% of all earthquakes occur. It is the Pacific Ring of Fire. And you can see it's not just on the west coast, but you can see that you have this ring-like area that encircles the Pacific Ocean. You have tectonic plates that are all over this area. And that is where 80% of all earthquakes occur. Now they call it Ring of Fire probably more because of the volcanoes that are there as well. Most of the Earth's volcanoes happen to be at the Ring of Fire also. But anyway, you can see that, I need to move this down a little bit when I flip back. What you can't see up here is it says a small percentage of earthquakes occur along faults within a plate. Here we have a map of where the darker where we have more earthquake probabilities. And you can see we've got all kinds of earthquake probabilities along the San Andreas Fault in California and up the coast, but you still have a fairly good probability here in Missouri. The New Madrid Fault in Missouri is not where a tectonic plate is. I mean, this is just a crack in this big plate here. And as a result, every once in a while you'll have an earthquake. It stems from there. You know, we talked about an earthquake in North Carolina that happened not long ago, and that we do have some every once in a while here in Georgia, and they all stem from this crack which is near New Madrid, Missouri. Do you ever have earthquakes in the asthenosphere? You know, the asthenosphere is below the lithosphere, and the answer is no. You do not have earthquakes in the asthenosphere. The asthenosphere isn't made of hard rock. You may remember that has like jello, tar-like, even caramel-like consistency. So if you have moving there, it just kind of absorbs any kind of stress or pressure there. But it's the rocks in the lithosphere which has a tough time absorbing that pressure. Earthquakes start beneath the Earth's surface. Now, one term we have is focus. The focus of an earthquake is the point underground where the rocks first begin to move. It actually starts at the focus. But whenever you hear on the news where it started, it's called the epicenter. The epicenter is the point on the Earth's surface directly above where the focus is, where it actually started. So it's just easier for us to understand something called the epicenter because we know where things are on the surface. We just don't know, we don't have names for things that are under the ground. One thing to note, that the closer to the surface that you have where the rocks actually move, the closest where the focus is, the more chance for damage. If you have a 5.0 that is closer to the surface, it'll create more damage than a 5.0 that is farther away from the surface. Here's a picture of a seismograph. A seismograph is an instrument used in measuring earthquakes. Now what they have, this is kind of an old-fashioned seismograph, but it's still the same premise. You have a pen which is on white paper. Now this white paper is constantly moving. They have it on rollers, so it's constantly going from one side to another. And you have this pen that is kind of strung in mid-air. You can see it's not being held by someone, it's held by something constant. This pole here, and it has the string come down with the pen. So what happens when the earth moves, this pen doesn't move. It moves back and forth the earth that is underneath it, where the paper is. So whenever you have a straight line, there is no earthquake activity, but when you have lines going back and forth, you have the ground that literally is moving, and that records it. That's a seismograph. Now today you have seismographs that are controlled more by computers, but it's the same premise. Let's talk about the Richter scale. You know, we talked a little bit about the Richter scale before. It measures the magnitude of these earthquakes. This scale increases of one whole number indicates an increase of 32 times more energy. I think I said that incorrectly in class. So if you go from a 4.0 to a 5.0 is 32 times more powerful than a 4.0. And you can see this is the chart we had in the book where it had 0.3 is rarely noticed, all the way up to, I think we saw a 7 point something on the earthquake chart the other day that was in Canada, where you would have some well-built structures destroyed, and an 8.0 or higher is just total destruction. Let's talk about earthquake damage. Often buildings, highway overpasses, and roads become cracked in earthquakes, and the problem is with earthquakes is going to be when you have cities and you have things falling down upon you. I mean, if we're inside a school and have an earthquake, it's the columns and the ceiling which could fall down us that could hurt us. If we're out in an open field, we're probably not going to get hurt. One part about earthquake damage is aftershocks. These are smaller earthquakes that follow a more powerful one. And sometimes aftershocks can be very strong. If you have a 7.5 earthquake, you might have an aftershock, which is a 6.9, which is still a very large, a fairly large earthquake. Sometimes in earthquakes you have fires that happen to get started with wires being twisted around. San Francisco had an earthquake in 1906, I believe it is. Most of the damage was fires. Landslides can happen because you have ground that has been loosened. It can shift the soil around. Topsoil can be gone farther down, and soil farther down can be going to the top. And you have the occasional tsunami, which we'll talk about more in a little bit. Here's some pictures of some earthquake damage. You see this building have the big cracks there, one side that has fallen down, debris all over the place. Here's some more earthquake damage, and the problem here is the debris. I mean, you see buildings around. All this came from debris which fell down. Here's crack in the road, big crack in the road. This actually happened in New England, from what I understand. Kind of uncharacteristic to have one there. And here you have this highway overpass, which is just destroyed. And I'm pretty sure this is from a 1989 earthquake in San Francisco. And the problem would not be out here in the open. The problem is if you're driving or anywhere close to this overpass right here. Okay, you can see here a picture of a tsunami. You have people literally running away from this huge wave. Here's another picture of a tsunami. Now, what happened is the earthquake didn't happen here where the tsunami is hitting. The earthquake happened many times hundreds of miles away. And what happens is you have the earth shaking where the earthquake is, and that causes the storm, not the storm, but it causes the vibrations to start a wave. Now the wave is not going to be this big out in the middle of the ocean, but it only gets that big closer to shore, and I'll tell you why in just a second. Here's more tsunami pictures. You have this wall of water and all these people which are going to have to get out of the way pretty soon there to survive. Okay, here's why you don't have such a big wave way out in the middle. Let's say you have an earthquake here under the water at some kind of fault. You can see the wave is still pretty small. But what happens is you have all this depth right here. All the energy can be stored up in this huge amount of depth. And whenever it gets closer to shore, you just have a small amount of depth. And all that energy is compressed into a small area. And that's when the wave starts getting higher. And that's exactly why that's the case. What can we do to prevent earthquakes? Well, it's very hard to predict them. I mean, we know that many of them will be in California and Alaska and around the Ring of Fire. We just don't know really good idea when they would be happening. So the best prevention is to build structures that can withstand earthquakes. Sometimes steel supports inside brick walls. The use of isolators, that's like flexible material that absorb the shaking, shear walls and shear core, braces in an X shape, lots of simple things that can be done.